So in this session, we're going to talk about the Newton-Raphson method, which is a method for finding the roots of a function, which are the points where it crosses the x-axis. So this particular method uses both the value of the function and the gradient of the function at each point in order to find your next approximation. So what I'm going to do is I'm going to explain it graphically first, and then hopefully we'll use that understanding to try and generate the equations that we require. So if we had a graph containing a function that looks something like this, okay? Let's just extend our axis out a bit here. So if we started with an initial guess, x0, but we were looking to find this root here, what the Newton-Raphson method does is says, okay, let's evaluate the function at our point, which is f of x0, and let's also evaluate the gradient of our function at that point, which is f prime of x0, okay? And using those two pieces of information, what we do is we construct a tangent line, which is the line that goes through the point, but also has the same gradient of the curve at the point. And our tangent line would look something like this. Okay, and once we've got that tangent line, we'll then use wherever the line crosses the x-axis as our next guess. So x1 is at this point here, and that's our next approximation to the root. And that's one complete iteration. And so now we can repeat that process. So we've got our point x1, we evaluate both the function and the gradient of the function at that point, and then we use those two pieces of information to construct a tangent line, which will look a bit like this. And that gives us our next approximation, x2 here. And you can see we're already pretty close to the root, and we can just keep repeating that method and getting closer and closer in. So I'll do one more line, which is going to look like this. And we're pretty much on top of the root now. Okay? So what we want to try and do now is construct the equation for these tangent lines to allow us to iterate. So all the tangent lines are straight lines, and all straight lines have an equation of the form y equals mx plus c, where c is called the y-intercept, and m is the gradient. Gradient and y-intercept. So, using these two pieces of information, we want to try and find m and c so that we can always construct these lines. So m is easy. M's the gradient. Well, we have the gradient of our function, so we just substitute that one in straight away. So y equals f prime of x0 times x plus c. Okay? And now we want to try and find the c. Well, to find c, we'd have to know y and x, but we do know y and x, because y and x are just the coordinates of a point on that line. And we have the coordinates, the x coordinate is x0, and the y coordinate is f of x. So we just sub those 2 points in, those two pair of coordinates in. F of x0 equals f prime of x0 at x0 plus c. And now we just rearrange and make it explicit for c. So c equals, I'm going to take this over here, so f of x0 minus f prime of x0 times x0. Okay? So now we've got our formula for c. We can sub it back into our full equation here, and we'll then have a complete equation for a tangent line on our curve that goes through the point x0, f of x0. So y equals f prime of x0 times x plus f of x0 minus f prime of x0 times x0. Okay, so here's our formula. And what we want to do with that formula, if you remember, is to find our next approximation. We want to know where this straight line goes through the x-axis. So where does it go through the x-axis? Well, that is at the value of y equals 0. So we just say 0 equals f prime of x0 times x plus f of x0 minus f prime of x0 times x0. And so with this, we want to now make this explicit for x, we want to know what value of x do you need to put in such that the value of y becomes 0. That's what we've just asked this equation. So rearranging it, what I'm going to do is put these two terms on the other side. So I'm going to say f prime of x naught times x naught minus f of x naught equals f prime of x naught times x. And then we're just going to divide through by this to leave x on its own. And we're going to get the following. We'll get that x equals f prime of x naught times x minus f of x naught, all divided by f prime of x naught. Okay? And so we've already given a name to this value of x. We've called it x1, which is our first guess. So x1, where the tangent line crosses the x-axis, is just the solution to this formula. So it's just using the x-coordinate, the value of the function of that x-coordinate, and the value of the function's gradient of that x-coordinate. And what we want to do now is write a general formula. So this gives us the first guess in terms of our initial guess, sorry, the first approximation in terms of our initial guess. And what we want to find is the n+1th approximation in terms of the nth approximation. So we can write that over here, and I'm just going to simplify it a bit. So xn+1 equals, and if you see, if we separate this fraction up into two terms, this would cancel with this, but we would be left with this fraction here. So we'll get xn+1 equals xn minus f of xn divided by f prime of xn. Okay? And we can now get rid of this bit. So that is the general Newton-Raphson formula. Okay? The next approximation is the current approximation minus this ratio of the value of the function and the function's gradient at that point. And what we're going to do now is just run through a quick example, numerical example. One very useful thing that you can do with root finding methods is very literally find the roots of numbers. So we're going to use it to find the square root of 2. Okay, so if we think about the graph, y equals x squared minus 2. So that's going to have a y-intercept at minus 2, but it's also going to have x-intercepts at minus root 2 and plus root 2. So this is the function y equals x squared minus 2. And clearly at y equals 0, you'll get 0 equals x squared minus 2. So x squared equals 2, and x equals plus or minus root 2. Okay? But we want to have a numerical approximation to this number. How do you actually find out what root 2 is? How do you go about working it out? So what we'll do is just follow this Newton-Raphson method. And we're going to start with our initial guess. It's intentionally not a very good initial guess. An initial guess of x equals 3. So x naught is 3. And let's draw a kind of zoomed in version of our graph on top of the board up here. So we've got the function, and it's going to look like this. So we'll go like this. Okay, and it obviously extends up over here as well. So if we say that x naught is over here, x naught, and we're going to say that our initial guess is x0, x naught equals 3. X naught equals 3. So starting from that point, we want to apply the Newton-Raphson method for 3 iterations. So we first want to take the general Newton-Raphson formula and convert it in terms of our specific function. So we're going to say that xn+1 is going to equal xn minus our function, which is x squared minus 2, divided by the differential of our function? Well, the differential of our function is just y prime equals 2x, right? X squared minus 2 just differentiates to 2x. So we divide by 2x, and we can simplify that a bit. These are both xn's. We can simplify and we can say xn plus 1 equals xn minus x squared divided by 2xn is just xn over 2, and minus 2 divided by 2xn is just plus 1 over xn. So the final sort of simple form for our Newton-Raphson method for this particular equation is going to be xn plus 1 equals xn over 2 plus 1 over xn. Okay? And we can now rub out these working steps. Right, so this equation is each iteration of the Newton-Raphson method for this particular function, y equals x squared minus 2. So let's start. So if we start with our initial guess of x naught equals 3. So at x naught equals 3, x1 is going to be 3 over 2 plus 1 over 3, which equals 3 over 2 plus 1 over 3. We can think about that. So times the top and bottom by 3 and top and bottom by 2, you get 11 over 6. So 11 over 6, which is roughly equal to, must be about 2, 1.83 recurring. Okay? So we started all the way over here at x naught equals 3, but applying our Newton-Raphson method, we've already come down to here, which is x1 equals 1.83 recurring. Okay, let's go again. So if x1 equals 11 over 6, then x2 is going to equal 11 over 12, that's 6 times 2, plus flipped 1 over 6, so 6 over 11, which equals 193 over 132, which numerical, so in decimal, that would equal 1.4621 with these last two digits recurring. Okay, and we'll apply it one more time. So x2 equals 193 over 132. So x3 is going to equal 193 over 264 plus 132 over 193, which equals, we'll forget about the fraction this time round, which equals 1.415, okay? And I hope most of you can spot that that's actually a pretty good approximation for the square root of 2 already. And I think I'm right in saying that that's within 0.1% of the real answer. So starting from a very poor initial guess, in just 3 pretty quick steps, in 3 quick iterations, we've already come very close. Something to think about is the fact that we've clearly found our positive root. Had we started from an initial guess of -3, we would have ended up with our negative root. And another thing to think about is, what if our initial guess had been 0? So 0 is actually closer to the roots than our initial guess of 3 really is. So 0 should work faster. But if you try and do it, what you'll find is that for this function, the gradient of our function at 0 is itself 0. It's flat at the bottom here, which means that when we look at our general Newton-Raphson formula, we'll see that we'd have to have a division by 0, which is not allowed. So the selection of your initial points not only governs which of your roots you'll find, but in some cases it'll mean that the method won't work at all. Okay?